I'd have gotten that backwards. But yeah, correct me, Alan. You got the floor.
Nailed it, brother. All right, cool. So we're going to go in with the prerequisites for the globe. So the biggest one being motion. So that's something that I'm going to cover. Okay, so kinematics means measurement. Kinematics means measurement. Kinematics means measurement. In kinematics, relative motion is true. Some kinematic variables that you might see are t, x, v, a, etc. So distance, velocity, acceleration, right? Those are all kinematic variables. Now, this is going to be important because we're going to be covering motion in the sky. So when things move in a circle, the kinematic relationship becomes extremely important because you can use these variables to describe the motion. For example, the acceleration of the stars must be equal to their velocity squared over the radius, right? So that's kinematics. Now, dynamics gets into the prediction of future motion based on real forces in that system. So the distinction there is kinematics is motion, irregardless of the cause of motion. It's just measurements of the motion, right? And then dynamics is predictions of future motion based off of real forces. In 1810 to 1818, a guy named Arago Francois did some experiments with a telescope to prove if the Earth was in motion or not. So what he did was, assuming a fixed ether and that light propagates through this stationary medium, the Earth would be moving through it, and you would have to adjust the focal length of your telescope to compensate for when viewing stars when you're receding or advancing towards them in 6-month intervals. What Arago found is that he didn't have to make any telescope corrections. So this is a huge failure for the dynamics of heliocentrism. If the motion that is required existed, it would be manifest in these measurements. Here's a summary of the second experiment that Arago did involving a telescope. So in this one, he half covered the telescope with a prism. What he was looking for there was to see if the aberration angle would change when the starlight was passing through just regular air and when it was passing through the prism. What he found was that the aberration angle is independent. It doesn't matter. It requires no further correction, meaning that the starlight is already coming in at an angle. So to further settle the matter, in 1872, George Airy came in with his telescope and to finally put this matter to rest, right? Who's moving? Is it us or the sky? So the situation here is the telescope requires a slight angle to keep starlight coming in at the center. If you were to fill the telescope with water, that would slow the speed of light down, and you would have to make additional corrections to keep the starlight in the center if the Earth's velocity is what was causing the deflection in the first place, right? So what Airy found was that he didn't have to make any further corrections. So that's a huge problem for heliocentrism. So here's the measurements that he put out. So this is in regards to Kinker-Fuse's hypothesis of an ether. So this is, again, a stationary ether, so that any corrections that are made to the telescope can be attributed to Earth's velocity. The important part to note here, this is not Airy didn't fail to detect the ether, right? This is a velocity measurement where the correction angle would be entirely attributed to the velocity to produce it, right? So they had a prediction that they were going to have to correct their telescope by 30 arc seconds when it was filled with water, and they only had to adjust it by 8 arc seconds. So it's another colossal failure for the dynamic predictions of motion for heliocentrism. Now, Kepler's laws and Newton's laws, they say are covariant, meaning you can derive one from the other, but it's actually just kind of a trick because the mass in these equations cancels out, and it's all about the constants. So the big G, the big N, and the T for the periodicity of the event will output a cubed proportional radius for the orbit, or for the semi-major axis for the orbit. And it's all cube proportional. It has nothing to do with the mass of any of these planets. So what they do everything in reference to the sun. So it'll be like the sun versus Mercury's orbit, or then the sun versus Venus's orbit, the sun versus Earth, etc. Right? All they're doing is just adjusting the periodicity of the event, and the constants remain the same. And the output gives them proportional orbital diameters, right? All right, so that's covering the sky optics and kinematics and dynamics. So in addition to that, if Earth's orbital velocity truly existed and Newtonian dynamics were correct, you could measure Earth's orbital velocity with interferometry with first order measurements, and no such measurements exist. 1887, Michelson-Morley attempted to make measurements of Earth's orbital velocity. They got 4 to 6 kilometers a second. Then Michelson, Gale, Pearson, where they were saying they were going to measure the sidereal rotation this time instead of the orbital velocity, because they gave up on that by this time, right? So they got fluctuations matching sidereal time measured in diurnal time. And this was another big failure for relativity, because the whole purpose of this was they were supposed to be calculating it based off of curved space-time, and they had to swap it in for flat space-time because they couldn't get enough inertial mass to curve space-time proportionally, right? So this was a failure for relativity to show that relativistic mass and inertial mass are equivalent, because the way that they had to do the calculations, it was a complete failure for them. Right, and then Michelson-Morley was continued by a guy named Dayton Miller, who found a porosity in the measurements. And when he did his final work, he started doing his measurements at altitude. So he did his last measurements at 8,200 feet above sea level, and found that the drift extent goes to 6 to 8 kilometers a second. And this was further corroborated in 2002 and 2004 by Yuri Galev, who showed using 2 radio links that there is a vertical velocity gradient that gets stronger as you get closer to the sky. So what he measured, he corroborated Miller's work. And how that works is that basically on the surface of the Earth, the speed goes, is greatly diminished. Then as you increase in altitude, you start getting a faster translational speed measurement, and it increases with the square root of the height above ground level. So we have the linear measurements here, starting from Michelson-Morley, 1887, and more of Miller's work, and then Galev's work. So we have a linear gradient that's going up, and that's my time. I'm going to kick it over to Toby now.
We have 3 globe claims. Essentially, we have the claim of motion, we have the claim of curvature, and we have a claim of geophysics. Just so in case you didn't know, if you believe in the globe, you also have absorbed all of these paradoxes: the particle wave duality, the twin paradox, the Ehrenfest paradox, the Einstein-Podolsky-Rosen paradox, Schrodinger's cat, Heisenberg uncertainty, Newman-Seliger gravitational paradox, the information paradox, Newton's shell theorem violation, also a violation of maximum momentum and minimum energy rotation, and also a violation of curved visual space, and many more. So let's start with motion here. So we feel no motion. All flight on Earth utilizes a stationary baseline. That includes planes, missiles, helicopters. Here we go. We have a flight simulation showing that they use a stationary Earth. Here we have dynamic positioning equations, and they show a non-rotating Earth. Here we have helicopter equations of motion, and they use a flat, non-rotating Earth. So a question: if pilots have to treat the Earth as stationary and we can't perceive any motion, is there any way we can measure it? Answer: yes, using the induction rate of light, which Alan just covered, we can measure absolute velocity as understood since at least 1818. In 1865, J.C. Maxwell worked upon Faraday's experiments, and he used known values of the electric constant and the magnetic constant in his electromagnetic wave equations, and he found that light behaves as an electromagnetic wave, which requires a substantive medium, aka the ether. And if you look throughout J.C. Maxwell's works, he repeatedly invokes the ether. It was a very well understood premise of all of science up until this point, and that's why in 1887, when they went to go do the Michelson-Morley experiment, they knew exactly what they were doing. They knew their math, they knew the induction rate of light, and so they used interferometry to measure the motion of the Earth. The independent variable would have been the orthogonal vector direction of the interferometer, and as they turned it, they would have got a difference in the fringe shift, and the result was that the Earth wasn't in motion. There was no orbital motion detected. There was a tiny bit of a fringe, and that tiny bit of fringe can actually be explained quite easily with a stationary Earth and an ether wind. So if we measure something to see if it's moving and we get no measurement, it's not moving, right? Well, no, not really, because Albert Einstein in 1905 on the electrodynamics of moving bodies, he says there's no ether, there's a one-way speed of light, and it's always constant. You're not allowed to invoke absolute space or absolute time. Everything's relative. And he says, he invokes imaginary physical experiments. That's how he derives special relativity. He talks about an unsuccessful attempt to discover any motion of the Earth relatively to the light medium, and then he invokes imaginary physical experience. That's how he derives special relativity. So then you got 0.9c plus 0.9c equals less than c, aka 2 plus 2 does not equal 4, because that's what Einstein told us with his crazy math. And then in 1913, George S. Sagnac came along and he said, hey, look, I'm going to rotate the interferometer. What do you know? As I rotate it, the proportional velocity of that rotation actually gets measured in the fringe shift. So it's actually not, the speed of light's not constant. It's measured proportionally to its velocity. And then in 1920s, Dayton Miller came and did a bunch more measurements. He actually started measuring with the interferometer over periods of time, and he found a preferred direction of the speed of light. The ether flow matches the motion of the sky, and the measurement is greater at altitude, and that's related to the motion of the solar system. But then in 1925, they came along and they tried to measure the exact same thing, even though they already measured it once. They said they got a null result. This time they measured it again. They said, oh, that's the rotation of the Earth. So then in 2001, Yuri Galev came along. And now all this time, they've never once acknowledged what Dayton Miller said, the fact that at higher altitudes, we actually get a greater ether wind. Galev came along, analyzed his work, found the same thing. Then Galev also did his own experimentation, which corroborated the exact same thing, which Alan already covered. And then in 2004, Ruyong Wang came along. Remember how they said you can only measure that velocity in a rotational vector? Well, guess what? Ruyong Wang explicitly showed that it's actually it can be shown with a linear vector. So if you can measure rotational motion of a linear vector, that means in 1887 they would have measured the motion of the Earth, but they didn't. So and he says here, this would suggest a nanoscale sensitivity. He patented a speedometer based off this exact thing, and he worked with the Naval Research Laboratory to do these experiments. They gave him money, they loaned him his fiber optic gyros that he used to do the experiments. So make of that what you will. But so let's move on now to the pendulum. In 1954, Maurice Elias observed anomalous behavior of his pendulum, and the effect was named the Elias effect. He observed it again in 1956, 1959. He wrote the anisotropy of space, necessary revision of certain postulates in 1997, and then this is showing the eclipse of 1959. You can see in the middle here where you can actually see the full totality of the eclipse, and you see that there's an anomalous behavior of the pendulum. And then he says this is totally inexplicable in the context of the current theory. And here it is again, 1955, another Elias effect. And it's so interestingly, not only did he measure the fact that the totally anomalous behavior during eclipses, but also the pendulum precession rate is relative to the sidereal motion of the sun and moon, aka their annual sky movement. So as the sun and the moon are moving back and forth on their analemma, that's actually affecting the way that the periodicity of not only interferometry as Dayton Miller showed, but also the precession of the pendulum. So that's completely inexplicable within the framework of currently accepted theories. This is translated by an AI from French. That's why it looks kind of weird. But here we have, it is therefore appropriate to consider that the current laws of gravitation are in no way perfectly verified, definitive, and immutable laws, on which basis the assertion that my experimental results are contrary to all the experience acquired in the field of astronomy. These laws, like all experimental laws, are only verified within a certain approximation. Here's showing what this would look like, right? So we have the sun going in the circle here. The moon would also be going in like a similar path, and this is what causes the motion and the shape of cyclones and hurricanes. It's also what potentially would be causing the precession of the pendulum. And in 1970, Saxel and Allen in Harvard, they measured the exact same thing. Here showing, this is a normal day. Here's a day with the Elias effect or with the solar eclipse. Wow. And they say results of this order of magnitude have been consistently observed at Harvard for a period of 17 years. And then here in 2006, another confirmation of it in Bucharest. Here 2010, they say they found no evidence of the Elias effect. Well, what do you know? They have an electromagnetic break, which keeps the electric trajectory in acceptable values. But, so they say the maximum deflection of the precession of the Foucault pendulum found in these measurements is very far from those obtained by Maurice Elias. But guess what? They never measure the break. So they're breaking out the Elias effect, and then they're not talking about it in the paper, and then they're making a conclusion. Cool. It's utterly meaningless. And then here's another paper where they just try to explain it. They're trying to explain the Elias effect, but, they come up with this crazy theory of dark flow acceleration. There's like this, they've got dark matter, dark energy. Now you got dark flow too, because you got to explain the precession of the pendulum. But so why are flat earth, they're so obsessed with relativity? Why are flat earth, they're so obsessed with the pendulum? Well, it's because all these things are intertwined with each other. And when you really, really, really start digging at all this stuff, you find that it's all wrapped around one line. You pull at that. And so that's why the ether wind's really important, just because if you look at this graph here, you see the ether wind's in the middle and gravity's in the middle. So let's get into curvature. So 2018, the FE coordinated laser test, they were taken in Hungary and in the Netherlands. There's the receiver where they were actually receiving the laser. Here showing the first laser test. This one, geoid undulation is the term used to describe the distance of the geoid or above or below the mathematical reference ellipsoid. Geoid undulation was at the same level in both positions. And the pointer was held 4.92 feet above the lake's surface. And it went across the lake 7.46 miles, and they were able to see it. And this is showing it would have had a hidden area of 14.96 feet, but they were able to see it. And here's showing this from the side view of measurement 1, showing the horizontal laser. And then we have measurement 7 from the same series of measurements. What's that?
1 minute left. Okay,
gotcha. So yeah, you get the point. They tried to measure, they couldn't see it, but we don't see boats go over the horizon. Where does the sun go at night? Well, it turns out we have optics, and we have curved visual space, and we perceive from a single point in 3D space. Angular resolution imposes a nonlinear drop off in our ability to resolve items as they move away from us. Your ability to ascertain objects dissipates into an unresolvable angle in a nonlinear fashion. And sixth grade art class actually taught us this. If you really think back to it, train tracks do not actually converge. This is a result of perceiving from a single point in 3D space. And so here's a paper about it. We say at the bottom, we will show binocular visual space may indeed be explained by a hyperbolic model. Here's showing kind of how that would look. Here's again showing how that would kind of look. And so, as you perceive outwards from here, as you can see, you are taking in more area. So as there's more area to take in, your resolution necessarily has to shrink because there's more coming in. And so here's a direct measurement of curved visual space. The curvature changes from elliptic in near space to hyperbolic at far space. At very large distance, the plane become parabolic. Here's an illustration showing that.
That's time.
What's that?
That's
time. Dang. Okay. I didn't get to get into geophysics. I wanted to talk about Pangea. I wanted to talk about magnetogeology. I wanted to talk about the geodynamo model and the fact that the rotational axis doesn't even align with the rotational axis of the convection currents. I wanted to talk about P and S wave shadow zones and how the S waves work on a flat Earth. But yeah, there's a lot to go through there.
All right. Yeah, it seemed like you had quite a lot of in the presentation there. So we'll ask you to stop the screen share there. Don't mind.